Okay, so I'm trying this out. I'm writing a book. I'm going to move. I'm writing a book, and I think I'm going to call it A Theory of Functional Programming. So let me explain. Here's the reasoning. Oh, that's bad lighting. Hold on. Okay. I'll explain what I'm doing, and then I'll explain the reasoning behind the book. So I want to write this book, and writing a book is hard. It takes a lot of time and energy. And you have to develop the ideas and type all the words and do everything. Um, and so any help I can get to do that will will be welcome. And someone suggested to me that I talk to someone or I record myself talking like in the car and then transcribe it. And it's not going to be great text or anything, but it'll be something to work with that will alleviate a lot of the typing that I'll have to do because editing is always easier than typing. And, we have a social part of our brain that helps us um, organize our ideas because we're able to think about what the other person is experiencing in a way that maybe when you're writing a book, it's good to do that, and it's often easy to slip out of that and just start writing very technical and abstract. So, uh, it's basically what I'm saying is it's easier to talk than it is to type. Somehow we can talk for hours and not really get tired of it, but typing for hours is tiring. So, why the book? So, functional programming has this very academic feel to it right now. When you do a Google search, all of the definitions, you search for something specific, you search for what is functional programming, you get a lot of definitions that basically boil down to functional programming is programming using pure functions. And so your whole program is a function from inputs to outputs. And I've been doing functional programming professionally since 2010. That's when I first started getting paid to do it. And I was doing it before that, just as on the side. But that is not how functional programs work. We actually do side effects. Our program is not one big function, one big pure function. There are effects in there, and that's actually the reason we write our program is to do all those effects. So there's something missing in that definition. The definition is also bad because when someone new to the field, someone in the industry, not in academia, my audience is more about people who are programming in industry, meaning commercial software. When they come over, when they see that definition, they they're turned off. Like, what does this add that the whole thing is one function? And what about emails, like sending emails? What about talking to another computer on the network? Um, that's it's an important aspect, and to just say we don't do that as functional programmers um, is turning them away. So it's incorrect, but it's also turning them away. Like it's making it seem like um, it's um, an impractical paradigm. So I want to do something about that. I want to have a good definition that I would be happy to point people to and hopefully other people would want to point people to as well. And so I looked at it a lot as helping functional programming escape the ivory tower. Meaning, it's in the ivory tower, it's trapped up, there's all this great knowledge, and now that it's kind of escaping into industry, we need to start talking more practical terms. That real software is not a function from inputs to outputs. It's something much more than that. So there's a ton of ideas here. So if I'm hesitating, it's because I don't know exactly how to continue. So let me take a moment here. Okay, why don't I just go right into the definition that I have? So functional programming is a paradigm, meaning it is a set of ideas, it's a set of concepts, a set of practices, and almost like a theory of programming itself. It is a framework, meaning a mental framework for how to approach a problem that you're trying to solve with software. So it is a paradigm like object-oriented programming is a paradigm. Object-oriented programming is a paradigm made up of, I'll just say three things. Like, I'll simplify it. So it's three things. It's objects, and those objects have references to other objects, and the objects can send messages to objects that they have references to. Okay, that's a very simple version of object-oriented programming, but that is, I think, a good nutshell summary of object-oriented programming. Functional programming is an orthogonal view. It is a totally different view of the same problem. Of the same, you can look at a problem through a totally different angle using functional programming. So when you're using object-oriented programming, what you can do is say, well, this object is going to do this thing, and then it'll solve this part of the problem, and then it'll send a message to this object, which will solve the next part of the problem, etc. And this one will talk to three other objects to solve the problem, and it's all the work is done through this messages traveling around the graph of objects, and finally the work is done, and you have the answer. So when you look at a problem in object-oriented view, you try to see where are my objects and what are their messages, right? Where do I do this work, and where do I do that work? What object is going to do that, and what message do I need to send to it to do that work, and what collaborators is this object going to have? And so when you are solving a problem like accounting, you might say, well, we'll make an object as the account will be an object, and you can send it a message like deposit, and it'll deposit a certain amount of money. Like that might be how you do it. I'm not solving that problem right now, but that's the approach you take. Is you start thinking, where do I cut this problem up into little objects that talk to each other? In functional programming, we have three different concepts. Those three concepts are data, calculations, and actions. So let's go over those three and give more definition for each one. So data is facts about events that have happened. So the event might be, I measured something on a scale, right? Or I took a reading from the thermometer, or this is the data that the user submitted in the form. It is data, it's a fact about an event that you can use for calculation or other uses, storage, record keeping, that kind of thing. And that's actually the easiest one to think about as a programmer. We use data all the time. So you've got your basic data like your numbers, characters, strings of characters. So you start talking about collections. You've got any compound data like tuples of numbers or strings or letters or bytes. All this stuff is lists of those things. They can nest. You can have hash maps. You can have whatever data. All of that is data. Okay, that's actually pretty easy to understand. And there's more to say about data, but I want to touch on the three things first. The next thing is calculations. So calculations are so I haven't found a good dictionary definition. I've looked in several dictionaries. They all talk about calculations as the act of calculating, and calculating is or calculations is the result of calculating, and calculating is the act of performing calculations. It's a bad definition. So I'm just going to also do a bad definition and just say it's all about computation from inputs to outputs. And those inputs, there's actually a rule of thumb. It's probably more than a rule of thumb. It's probably a little bit stricter than that, but the idea behind the calculation is that it is timeless. So given the same inputs, you will always get the same outputs. Okay? And it doesn't matter when you run it or even if you run it. Right? This is what we often call in functional programming in the academic world, we call it a pure function. It is the mathematical sense of function, which is a relation between the argument to its value. Or a relationship between the domain and the range, if you wish. That's a much more mathematical way of saying it. Okay, and so in the final one is the actions. Now these are often called effects or side effects, but I think that the term effect is a little bit, it's a poor term because I'm not talking about the effect. I'm not talking about the email being sent. I'm talking about an action which is a representation of that email being sent, which you can then invoke that action, and that causes the email to be sent. So the effect is actually the cause, the action is the cause and the effect is, what happens. Action is the cause of the effect. It's not the email being sent, it is a thing that represents the email being sent, and when you invoke it, it will send it. And in that way, you can manipulate it in a way that you can't manipulate an email being sent normally. You can manipulate let's say, a Java method that will send the email, right? You can talk about that more abstractly. So the way you tell if something is an action is it matters when you invoke it or how many times, or both. So, a good example is sending an email. It's a very good example. If I send 0 emails, it's different from sending 1 email, right? The effect on the world is very different. And it's also different if I send 2 emails, or send 3 or a million emails. Like, all of those things are going to have much different effects on the world. And it matters when I send it. If I send the email now, it's different from sending it in 2 weeks. I can't, I can't change that. That's part of the way the action works. We'll get to this later, but some actions, doesn't matter when you call it, but it matters how many times you call it. And some actions, it matters when you call it, but it doesn't matter how many times you call it. So that's, there's ways to like compartmentalize these actions. Okay, so those are the 3 things: data, calculations, and actions. And they are the principal domains, I'm calling them. I don't know if that's a good word, but for now, domains. That's the principal domains of functional programming. And doing functional programming, programming in a functional way, means approaching a problem with these 3 domains in mind. So as an object-oriented programmer would look at the problem and say, where are my objects, and what are my messages, and what objects know about what other objects, etc. A functional programmer says, well, where's the data? What data can I get from, events happening in the world? And how do I calculate those things? And then what actions does the system need to take? Okay, now there's more. There's a lot more. Hence, I'm writing a book. Like, it's not going to be as easy as just listing this stuff like this. So the other thing about functional programming is that everything is first class. So when I say everything, there's only 3 types of things. So there's data, there's data, calculations, and actions. And the reason I'm staying away from using the term function is because in industry, it's kind of been, it's a feature of languages. And I'm trying to avoid talking about features. Because functional programming is not about features, it's about this mindset. And if you talk about if you start talking about features like I need functions, then you think, well, does something like Java have real functions, right? So I'm trying to avoid all things that are tied up in the notion of features. But you do need certain features to be able to do functional programming. The features that you need, the real feature you need is that everything has to be first class. And by first class, I mean you have to be able to pass all 3 types of things as arguments or return them as return values to your functions or your subroutines or whatever feature you have. So you have to be able to get a handle on them somehow, some kind of handle on them. First class, you have to be able to hold them. Because the principal way we write programs in functional programming is by composing these things. And we'll talk about composition in a minute. So, without being able to have first-class actions and calculations, usually data is first class, so I'm just going to kind of ignore that. But without having to have them as first-class things in your language, you can't do functional programming. But often, you can get around limitations. So if you're doing JavaScript, your data, that's easy. It's your numbers, it's your strings, it's your objects and your arrays. And you don't have much more than that. Your booleans, I think that's it. And your null. So that's your data. How do you do calculations? Well, in JavaScript, you have to write functions, and you have to ensure that they are pure. Ensure meaning, you know, trust yourself that you'll write them pure. Because there's no type checker or anything to help you. There's no static analysis that does that. So you write a pure function, and that can be a calculation. And then your actions are your impure functions, all the other functions that do it. And as a function, you can be first class. But there are things in JavaScript that are not first class that you need to be first class. For instance, the plus operator, addition, and all the mathematical operators like that, the times, divide, minus, those are not first class. You cannot pass plus to another function. But you can wrap up the plus in a function that takes, two arguments, or however you want to do it. But it now becomes a function called plus, plus spelled out, that you can use instead of the arithmetic operator plus that is not first class. Similarly, in a language like Java, you can wrap something up as an object with a method, or you can work around the parts of the language that are not first class. But typically, and that lets you do functional programming in those languages. Typically, you do in a functional language, all of that is taken care of for you. Everything is first class by default, and you don't have to worry about that. I say everything. All of the three types of things, right? Because some languages might provide something else. I'm thinking type systems. Like in Haskell, the types are not exactly first class. They're on a different class, a different level than all the values. But all your data are values, and you have a bunch of types, different like built-in types. But then you also you can write your own types. All that's data. And then you have all your functions are pure by default. So that really helps. You just say functions in Haskell. You don't have to say pure functions. And then then you have your actions. That's the I/O type. So there's a special type that is just for actions, which is really nice. Haskell provides just what you need for that triple separation there. Now in Clojure, which is what I write in, you have the data. And it provides a lot of data, and like a lot of data structures and types that you would want to use. But then you have to do, just like in JavaScript, you have to separate out by hand, in your mind, what are the pure functions and what are the impure functions. Because the pure functions are the calculations and the impure functions are the actions. But Clojure programmers get quite good at doing that. And so Clojure programmers are comfortable with that lack of, compiler help on that front. So it's entirely possible, my point is that it is entirely possible to not have help from the language separating out those actions from the calculations. But it doesn't, it's certainly helpful to have that. Sometimes I want it. I'll tell you that. Okay, so I said I was gonna talk about composition. So we have these three domains, and you might think at this point that it's quite obvious that this is obviously what these domains obviously make sense. But I would say that that's not the case for other paradigms. Like, people do not think in these terms in other paradigms. In object-oriented programming, for instance, which we've already gone into, they're not thinking about whether a message pass is an effect or if it's pure or something like that. Like, there's no easy mapping between the three. So this isn't something that I'm not saying it's incompatible. I'm saying that the way you cut things up, like, okay, the two views cannot be reconciled with each other. So if I do an object-oriented analysis, I cannot transform that into a functional programming analysis. I can't. There's no way to do that. I can do both analyses of the same problem and have two perspectives, which will help. By having multiple perspectives, I can now see more about the problem and probably solve it better. But I can't do that. I can't do that isomorphism, right? I can't do that simple transformation between the two. So both, they're not incompatible in that I can do both on the same problem, and both will help me solve the problem and arrive at a better solution. But one might not inform the other because they're totally different perspectives on the same problem. And so I hope that it being obvious is more a product of it being super clear. And I guess also I want to say, even if it is obvious and everyone already knows this, no one has written it down. And so I'm going to write it down in a book. Yeah, that's all I have to say about that. Okay, the next thing I want to talk about is the three domains. And I kind of feel like when you do one of these theories like this, where you try to build a coherent model, it's easy to like draw some lines, some boxes, and say this is where everything goes. And have you really captured something by giving a couple of rules for what goes in which bucket? And so I feel like it would be justified to come up with some evidence that these things make sense, that each domain is coherent in itself. So what I want to say is that that you can actually stay in a domain. So there are operations that will take data, like two pieces of data, compose them, and give you a third piece of data. What those two data can't do is give you an action. Or you could make up an action for those pieces of data, but you can stay in that domain, right? And so that you can have data that turns into more data, that transforms into different data, that gets added to other data, and you're just always in data. And you can do the same for calculations. I can take a function, and I can compose it with another function, and I can do the complement of that function, and then I can transform it into another function, and I can, so as long as I'm just doing functions, I can stay in this arena of functions, calculations, right? So there is a coherency to this division. And it's borne out also by, languages like Haskell that have this strong division. There's the data, all the data types, and then there's the function types that, all the different, it's polymorphic, but there's the functions, and then there's the I/O, which is the actions. It's a separate thing, it has its own rules. Right. Okay, and so then the same goes with actions. I can take two actions, I can compose them, I can reverse them, I can run them in parallel, I can add another action. And you can just stay in this domain of actions. All right. So why are actions so one rule when doing functional programming that you'll quickly learn is that you want to do as little work as possible in actions, right? And this is the source of a lot of the bad definitions of functional programming. And I say bad meaning they're technically correct if you already understand functional programming, and you can kind of squint and say, yeah, I understand what he's trying to say, he or she. I understand what they're trying to say. I got it. Avoid side effects. Avoid side effects. Okay, I see what you mean. Like, if you can do it in a function instead of in I/O, that makes sense to a functional programmer. But it's not a good definition in that it doesn't help someone who doesn't already know learn it. What a lot of these bad definitions say is avoid side effects, or functional programming is doing your best to describe your problem in terms of pure functions. You notice there's always this focus on the functions, and they forget about the data and they forget about the actions, right? So why is that? Well, it turns out that when you diagram it, that actions are the universal thing, right? Our machines are based on the Turing machine, and the Turing machine is actually, all it does is actions. It moves the tape back and forth. It reads and writes to the tape. And so everything is actions. The fact that you get a calculation out at the end is kind of like the mystery of computation, and it's sort of what he was trying to get at. Turing was trying to get at. So it's a cool thing, right? That you can do some actions in the world, and you've calculated, you solved a problem. And it's what allows us to think and solve problems through thinking, is that our brains are sending signals, and all these actions are happening, these timely things. It's all timely. Like, if the thing fired tomorrow, my brain fired tomorrow, I would have a different thought, and it would be too late, or it would be the wrong thought at the time, and I wouldn't solve the problem that I'm solving now, etc. So it's all timely, so it's actions. But we get an answer out at the end, which is really cool. So when a procedural programmer is like, I can't program without side effects, I need it. Well, you can't, they're right. You do need effects, right? We do need to send that email. We do need to write to the disk. We do need to, send a message over the network. We need to do those things. So actions are universal. We know we can represent functions in terms of actions. And we also know through the lambda calculus that we can represent data in terms of functions. I don't want to go into that, but with pure functions, I don't want to go into the lambda calculus part, but with pure functions, you can represent any data value. It's totally feasible. So actually, data is a subset of functions, a subset of calculations, and calculations are a subset of, I'm running out of battery. Calculations are a subset of actions. But functional programmers appreciate the value of moving as much of your code down that um, hierarchy as much as possible into data. And what you can't get into data, try to get into calculations. And what can't be calculations, as actions. Okay, I'm gonna stop now. This has been 35 minutes. I'm getting kind of tired. There's more to talk about. I'm getting excited because this is cool stuff. All right, subscribe because I'm gonna keep talking about this. I'm gonna be using this I'm gonna transcribe it and use it as part of my book. I'll probably post it to my blog and everything. So keep listening, subscribe, like, and check out the book when it comes out.